Hello there, and welcome to the Dreamy Science Guy. I'm so glad you found your way here tonight. Maybe you've had a long day, filled with meetings and obligations, or perhaps you're dealing with the quiet weight that sometimes settles on us in the evening hours. Or maybe you're just the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep, who finds peace in pondering the vast scales of space and time. Either way, tonight's journey is designed especially for you. You've got nothing to do but rest. No tasks await you. No decisions need to be made. Just let your mind relax, your breathing slow naturally, and your body grow light as if gravity itself has softened its hold on you. Think about it for a moment. Every morning, for as long as life has existed on this planet, the sun has risen. Every evening it has set. This rhythm has continued without fail for billions of years. It continued through the age of the dinosaurs, through the ice ages, through humanity's entire existence. It continued yesterday, it's continuing today, and it will continue tomorrow. There's something deeply comforting in that constancy, in knowing that some things in this universe are reliable beyond measure. We'll learn about the sun's spots and flares, those dramatic events that occasionally disrupt our communications and create beautiful auroras in the polar skies. We'll discover its 11-year cycle of activity, a cosmic heartbeat that has pulsed steadily for as long as the sun has burned. We'll explore the invisible solar wind that streams from the sun's corona, filling the entire solar system with charged particles. And we'll look ahead to the sun's future, billions of years from now, when it will swell into an enormous red giant, perhaps engulfing the inner planets, before finally shedding its outer layers and fading quietly into a white dwarf, a dense ember that will slowly cool over trillions of years. Some of what you hear tonight might surprise you. You might learn facts you've never encountered before, or see familiar things in a new light. Or perhaps you'll simply find these thoughts soothing, gentle companions as you drift towards sleep. The universe is vast and old and strange, but it follows rules we can understand. There's a kind of peace in that, in knowing that even something as enormous as the sun operates according to principles we've figured out, laws of physics that are the same everywhere in the cosmos. And just before we begin our journey, if these calm, curious explorations help you unwind after your day, or give you a peaceful way to end your evening, consider liking this video and subscribing to the channel. Every like and subscription helps other people find their way here too, helps them discover these gentle voyages through science and space, one sleepy soul at a time. It's a small thing, but it makes a difference, and I'm grateful for it. Now, with that said, let's begin. Let's start at the beginning, billions of years ago, in a cold, dark cloud floating through space, and watch as that cloud transforms into the star that makes our world possible. The sun's place in our lives. The sun rises every morning, painting the eastern sky in shades of pink and gold. It climbs through the day, tracking across the dome of the heavens, and sets every evening, leaving behind a blaze of orange and purple. This rhythm, this daily dance of light and shadow, has been the most constant thing in human experience for as long as our species has existed. Longer than that, actually. This rhythm has continued for billions of years, since long before humans walked the earth, since before there were mammals or dinosaurs or even complex life at all. It warms our skin when we step outside. It lights our days, allowing us to see the world in all its colours and details. It makes life itself possible, in ways both obvious and subtle. Without the sun's energy, Earth would be a frozen ball of rock drifting through the cosmic darkness, with temperatures hovering around negative 270 degrees Celsius, just above absolute zero. There would be no liquid water, no atmosphere as we know it, no weather, no seasons, no plants growing toward the light, no animals grazing or hunting, no cities humming with activity, just ice, rock, and eternal night. We take the sun for granted most of the time, and perhaps that's natural. The sun is just there, a familiar presence, reliable and constant. It's a glowing disk in the sky, sometimes bright and sometimes hidden behind clouds, but always present somewhere above us. We go about our days without giving it much thought. We might notice it when it's particularly beautiful, during a stunning sunset or when its rays break through storm clouds in dramatic beams. But most of the time, the sun is simply part of the background of existence, as unremarkable and taken for granted as the air we breathe. And yet, when you really stop to think about what the sun is, When you truly consider it, the sun becomes one of the most extraordinary things in our experience. The sun is not just a light in the sky, some celestial lamp hanging overhead. It's a star, an actual genuine star, just like the countless pinpricks of light you see in the night sky when you look up from a dark place far from city lights. The difference is distance. Those other stars are so far away that their light takes years, decades, centuries, even thousands of years to reach us. The sun is close, astronomically speaking. It's our star, the star that Earth orbits, the anchor of our solar system. The sun is a massive ball of hydrogen and helium, held together by its own gravity, powered by nuclear fusion reactions deep in its core. Its mass is almost unimaginable. It contains 99.86% of all the mass in our entire solar system. Think about that for a moment. Everything else, absolutely everything else, all 8 planets from tiny Mercury to giant Jupiter, all the hundreds of moons, all the asteroids in the asteroid belt, all the comets in the Kuiper belt and Oort cloud, all the dust and gas and every speck of matter in the solar system combined, makes up less than 1/5 of 1% of the total mass. The sun dominates the solar system not just in brightness, but in sheer physical presence. If you could somehow gather up all the matter in the solar system and weigh it, the sun would account for more than 99 parts out of every 100. The sun is enormous in size as well as mass. Its diameter is about 1,391,400 kilometers. To put that in perspective, that's roughly 109 times wider than Earth. If you could line up Earth side by side across the face of the sun, you'd need 109 of them to reach from one edge to the other. And if you could hollow out the sun, creating an enormous empty sphere, you could fit about 1 million Earths inside it. 1 million Earth-sized planets, all nestled within the volume of the sun. It's difficult for our minds to grasp such scales, but that gives you some sense of the sun's immensity. When you look at the sun, even though it appears as a relatively small disk in our sky, roughly the same angular size as the moon, despite being 400 times larger and 400 times farther away, you're looking at something so vast that light itself, travelling at 300,000 kilometers per second, the fastest speed possible in our universe, takes nearly 5 seconds to cross from one side of the sun to the other. 5 seconds doesn't sound like much, but at the speed of light, it's an enormous distance. In 1 second, light travels far enough to circle Earth's equator 7.5 times. In 5 seconds, it crosses the diameter of the sun, and yet, for all its size and mass and power, by cosmic standards, the sun is completely unremarkable. It's what astronomers classify as a G-type main sequence star, a star on the middle of its life cycle, steadily fusing hydrogen into helium in its core. It's often informally called a yellow dwarf, though this name is somewhat misleading because the sun's light is actually white when viewed from space, and the sun is neither particularly small nor actually yellow. But it has become a common term, so we use it. Among the estimated 200 billion stars in the Milky Way galaxy, the sun is neither especially large nor especially small, neither particularly hot nor particularly cool, neither remarkably bright nor especially dim. It's average in almost every measurable way. There are stars out there that are hundreds of times larger than the sun, supergiants so enormous that if you placed one at the center of our solar system, its surface would extend past the orbit of Mars. There are stars that are smaller than some planets, neutron stars compressed to the size of a city but containing more mass than the sun. There are stars that are thousands of times brighter than the sun, and stars that are thousands of times dimmer. But our sun sits comfortably in the middle, unremarkable, ordinary, typical. And yet, for us, for everything and everyone on Earth, the sun is everything. It is the most important object in our sky, the most important object in our entire existence. Without it, none of this, nothing we know, would exist. The sun lies at the exact center of our solar system, holding everything in its gravitational embrace. About 93 million miles separate Earth from the sun, or roughly 150 million kilometers. This distance is so commonly used in astronomy that it has its own name, 1 astronomical unit, or 1 AU for short. When astronomers talk about distances within the solar system, they often use AU as their unit. Mars orbits at about 1.5 AU from the Sun. Jupiter is at about 5.2 AU. Neptune, the outermost planet, orbits at an average distance of 30 AU. Beyond that lie the Kuiper Belt and the even more distant Oort cloud, regions filled with icy bodies and comets extending thousands of AU from the Sun. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth, travelling at the cosmic speed limit of 300,000 kilometers per second. This means that when you look at the Sun, assuming you're using proper eye protection and not looking directly at it, you're not seeing it as it is at this very moment. You're seeing it as it was 8 minutes and 20 seconds ago. The Sun you see in the morning sky has already moved on by the time its light reaches your eyes. If the Sun somehow vanished, disappeared completely from existence, we wouldn't know it for 8 minutes. The light that was already on its way would continue travelling toward us, and for 8 more minutes, everything would seem normal. Only after that delay would the sky go dark and we'd realise something catastrophic had happened. This distance, this 93 million miles, turns out to be remarkably well suited for life. It's what astronomers call the habitable zone, sometimes poetically referred to as the Goldilocks zone, not too hot and not too cold, but just right. If Earth was significantly closer to the Sun, temperatures would rise dramatically. Water, the basis of all life as we know it, would evaporate. Our oceans would boil away into space, leaving behind a dry, scorched world more like Venus, where surface temperatures reach over 450 degrees Celsius, hot enough to melt lead. If we were farther away from the Sun, Earth would be too cold. Water would freeze solid. The atmosphere might condense and snow down onto the surface as frozen air. We'd become an ice world, perhaps something like Jupiter's moon Europa, with a frozen surface and any liquid water buried deep beneath kilometers of ice. But Earth orbits at just the right distance. We're warm enough that water remains liquid for most of the year across most of the planet, creating the oceans that cover 70% of Earth's surface and the rivers and lakes that sustain life on land. We're cool enough that this water doesn't simply evaporate away. This balance, this perfect positioning in the habitable zone, is one of the key factors that makes Earth unique in our solar system. The only world where liquid water flows freely on the surface, the only world teeming with life. The Sun's energy reaches Earth primarily as light and heat, electromagnetic radiation spanning a broad spectrum from infrared to visible light to ultraviolet and beyond. This energy drives nearly every process on Earth's surface. It powers the water cycle, that endless circulation of water between the oceans, the atmosphere, and the land. Solar radiation heats the oceans, causing water molecules at the surface to evaporate and rise into the atmosphere as water vapor invisible and light. As this moist air rises and cools, the water vapor condenses back into liquid droplets, forming clouds. The clouds drift with the winds, and when conditions are right, they release their moisture as rain or snow. The precipitation falls to the ground, flows into streams and rivers, and eventually returns to the oceans, completing the cycle. This cycle distributes fresh water across the continents, watering forests and grasslands, filling lakes and rivers, making agriculture and civilization possible. The Sun also drives the circulation of Earth's atmosphere, creating the winds and weather patterns that shape our daily experience. Solar heating is strongest at the equator, where the Sun's rays strike most directly, perpendicular to the surface for much of the year. The air at the equator warms, becomes less dense, and rises, creating a region of low atmospheric pressure. This rising air spreads out at high altitudes and moves toward the poles, where it cools, becomes denser, and sinks back to the surface, creating regions of high pressure. The cool air then flows back toward the equator at low altitudes, completing the circulation. But this simple pattern is complicated by Earth's rotation, which deflects the moving air through the Coriolis effect, creating the trade winds, the westerlies, and the polar easterlies that sailors and meteorologists know so well. These global wind patterns, all ultimately powered by the Sun's uneven heating of Earth's surface, determine our climate zones, influence our weather. The Sun is enormous. Its diameter is about 1,391,400 kilometers, roughly 109 times wider than Earth. If you could hollow out the Sun and fill it with Earths, you could fit about 1 million of them inside. Its mass is about 330,000 times that of Earth. When you look at the Sun, even though it appears as a small disk in our sky, you're looking at something so vast that light itself takes nearly 5 seconds to travel from one side of it to the other. And yet, by cosmic standards, the Sun is unremarkable. It's what astronomers call a G-type main sequence star, often informally referred to as a yellow dwarf, though its light is actually white. Among the 200 billion or so stars in the Milky Way galaxy, the Sun is neither especially large nor especially small, neither particularly hot nor particularly cool. It's average in almost every way. But for us it is everything. The Sun lies at the centre of our solar system, about 93 million miles from Earth, or 150 million kilometres. This distance is called an astronomical unit, and it's used as a standard measure in astronomy. Light from the Sun takes about 8 minutes and 20 seconds to reach us, travelling at 300,000 kilometres per second. That means when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. The Sun you see in the morning sky has already moved on by the time its light reaches your eyes. This distance is perfect. If Earth were significantly close to the Sun, temperatures would be too hot for liquid water to exist. If we were farther away, we'd be too cold. The Sun's energy reaches Earth as light and heat, driving the weather, the seasons, and the cycles of life. Plants capture its light through photosynthesis, converting carbon dioxide and water into sugars and releasing oxygen as a byproduct. This oxygen is what we breathe. The food we eat, whether from plants or animals, ultimately derives its energy from the Sun. Even the fossil fuels we burn are stores of ancient sunlight, captured by plants millions of years ago and transformed over time into coal, oil, and natural gas. The Sun's gravity holds our solar system together. It keeps Earth in its orbit, along with the 7 other planets, hundreds of moons, countless asteroids and comets, and vast clouds of dust and gas. Without the Sun's gravitational pull, everything would drift apart, flying off into interstellar space. We orbit the Sun at a speed of about 30 kilometers per second, completing one full orbit every 365.25 days. This is what we call a year. Throughout human history, people have worshipped the Sun as a god. Ancient Egyptians revered Ra, the sun god who sailed across the sky each day. The Aztecs believed in Tonatiuh, whose hunger for sacrifice sustained the sun's journey. The ancient Greeks had Helios driving his chariot across the heavens. These myths were humanity's way of acknowledging the sun's power and importance, of trying to understand the force that gave them light and warmth. It wasn't until the 17th century that scientists began to understand the sun more clearly. Galileo used his telescope to observe sunspots, dark patches on the sun's surface that seemed to move across its face. This showed that the sun wasn't a perfect unchanging sphere but a dynamic object with features that changed over time. Over the next few centuries, astronomers learned that the sun was not at the edge of the universe, but simply one star among countless others, and that it was not Earth that sat at the centre of everything, but the sun itself at the heart of our solar system. Today we know much more. We know the sun is a star powered by nuclear fusion. We know its age, its composition, its temperature. We've sent spacecraft to study it up close, measuring its magnetic fields, its eruptions, its winds. We've learned that the sun has a cycle of activity that repeats roughly every 11 years, marked by changes in the number of sunspots and the frequency of solar flares. We know that it was born about 4.6 billion years ago, and that it has roughly another 5 billion years left before it begins to die. But even with all this knowledge, the sun remains something mysterious and awe-inspiring. It's a reminder of the power and beauty of the universe, a beacon of light and warmth in the cold darkness of space, and it's the reason we're here at all. The sun's birth and origins. About 4.6 billion years ago, in a quiet region of the Milky Way galaxy, there was a vast cloud of gas and dust. This cloud, called a molecular cloud or nebula, was made mostly of hydrogen and helium, the two simplest and most abundant elements in the universe. Mixed in with these gases were tiny grains of dust, particles of heavier elements like carbon, oxygen and iron that had been forged in the cores of earlier generations of stars and scattered into space when those stars died. The cloud drifted through the galaxy, cold and dark, spanning light years across. It was a quiet place, unremarkable, just one of many such clouds scattered throughout the Milky Way. But something happened to disturb its peace. Perhaps a nearby star exploded in a supernova, sending shockwaves rippling through space. Perhaps the gravitational pull of a passing star tugged on the cloud, compressing part of it. Or perhaps the cloud simply reached a critical density where its own gravity began to overwhelm the outward pressure of its gas. Whatever the cause, a portion of the cloud began to collapse. Gravity pulled the gas and dust inward, toward the centre. As the material fell, it began to spin faster, much like a figure skater pulling in their arms to spin more rapidly. The spinning caused the collapsing cloud to flatten into a disk, with most of the mass concentrated at the centre. This was the solar nebula, the birthplace of our Sun and everything in our solar system. At the centre of this disk, the density and temperature began to rise. As more and more material piled on, the pressure increased. The hydrogen atoms at the core were squeezed closer and closer together, moving faster and faster, colliding with ever greater energy. The centre grew hot, glowing first with a dull red light, then brighter and brighter. This was the proto-sun, a young star in the making. For hundreds of thousands of years, the proto-sun continued to grow, pulling in gas and dust from the surrounding disk. It wasn't yet a true star. It was simply a hot ball of gas, heated by the energy of gravitational collapse. But deep in its core, conditions were becoming extreme. The temperature climbed to millions of degrees, the pressure became immense, and then something remarkable happened. The hydrogen atoms at the core, stripped of their electrons and reduced to bare protons, began to fuse together. Two protons collided with enough energy to overcome their natural repulsion and bind together, forming a deuterium nucleus. This deuterium quickly captured another proton, forming helium-3. Two helium-3 nuclei then collided, fusing to create helium-4 and releasing two protons in the process. This chain of reactions is called the proton-proton chain, and it releases enormous amounts of energy. When the fusion reactions ignited, the proto-sun became a true star. The energy released by fusion created an outward pressure that balanced the inward pull of gravity. The sun stopped collapsing. It found equilibrium, a stable state, where it could burn steadily for billions of years. The sun was born. But the sun's birth was not a solitary event. Around it, in the remaining disk of gas and dust, other processes were underway. Small particles of dust collided and stuck together, forming larger and larger clumps. These clumps grew through a process called accretion, pulling in more material as they orbited through the disk. Over millions of years, these clumps became planetesimals, objects ranging from meters to kilometers across. The planetesimals collided with each other, sometimes shattering, sometimes merging, gradually building up into larger bodies. In the inner part of the disk, close to the young sun, temperatures were high. Only materials that could withstand the heat remained solid, substances like rock and metal. This is where the rocky planets formed: Mercury, Venus, Earth, and Mars. Farther out, where temperatures were cooler, water ice and other volatile compounds could remain solid. This is where the gas giants formed: Jupiter and Saturn, and the ice giants Uranus and Neptune. These outer planets grew massive enough that their gravity could capture and hold onto vast amounts of hydrogen and helium gas from the surrounding disk. The sun's early years were turbulent. As a young star, it went through a phase called the T Tauri phase, marked by intense stellar winds and powerful magnetic activity. These winds swept through the solar system, clearing away much of the remaining gas and dust. What was left behind were the planets, moons, asteroids, and comets that we see today. The sun itself settled into a long, stable period of burning hydrogen in its core. This is the main sequence phase, the stage of stellar life where stars spend most of their existence. For a star like the sun, this phase lasts about 10 billion years. The sun has been on the main sequence for roughly 4.6 billion years now, meaning it's about halfway through this stable period. The supernova that may have triggered the sun's birth also left traces. Among the ancient meteorites that formed in the early solar system, scientists have found isotopes of certain elements, like iron-60 and aluminum-26, that could only have been produced in a supernova explosion. These isotopes have very short half-lives, meaning they decay quickly. The fact that they were present in the early solar system suggests that a supernova occurred nearby, perhaps within a few light years, shortly before the sun formed. The shockwave from this explosion may have compressed the molecular cloud, starting the collapse that led to the sun's birth. Some scientists believe the sun formed not in isolation, but as part of a star cluster, a group of hundreds or even thousands of stars born together from the same cloud, over time. These clusters disperse as the stars drift apart, pulled by the gravity of the galaxy and by close encounters with other stars. If the Sun was part of such a cluster, its siblings are now scattered across the Milky Way, indistinguishable from the countless other stars that fill the night sky. Finding these sibling stars is one of the goals of modern astronomy, a search for distant relatives born from the same cloud as our Sun. The Sun's birthplace is long gone. The molecular cloud that gave it life has dispersed, blown away by stellar winds and the radiation of young stars. But the evidence of that birth remains, preserved in the meteorites that fall to Earth, in the composition of the planets, and in the Sun itself. When we study the Sun, we are looking back at the conditions of the early solar system, learning about the processes that shaped our world and made life possible. The Sun's structure. A journey through layers. The Sun is not uniform. It's not a solid object like a planet or a moon. Instead, it's a ball of plasma, a state of matter where atoms are stripped of their electrons, leaving a hot, churning sea of charged particles. The Sun has distinct layers, each with its own characteristics, its own role in the grand process of generating and transporting energy from the core to space. Let's begin our journey at the center, in the Sun's core. This is where everything starts, where the Sun's energy is born. The core extends from the very center of the Sun out to about 25% of the Sun's radius, roughly 175,000 kilometers from the center. This may sound like a large region, but it's actually quite small compared to the Sun's total size. Yet this small core produces virtually all of the Sun's energy. The conditions in the core are extreme. The temperature is about 15 million degrees Celsius, or 27 million degrees Fahrenheit. The pressure is about 250 billion times the atmospheric pressure here on Earth. Under these conditions, hydrogen nuclei stripped bare of their electrons are squeezed so tightly together that they overcome their natural repulsion and fuse into helium. This is nuclear fusion, the same process that powers hydrogen bombs, but occurring on a scale almost beyond comprehension. Every second, the Sun converts about 600 million tons of hydrogen into helium. Of this mass, about 4 million tons are converted directly into energy, according to Einstein's famous equation, E equals mc squared. This energy is released in the form of gamma-ray photons, high-energy particles of light. The gamma rays begin their long journey outward from the core, but they don't travel in a straight line. They're constantly absorbed and re-emitted by the plasma, bouncing around in random directions. This process takes a very long time. A single photon might take anywhere from 10,000 to several 100,000 years to make its way from the core to the surface of the Sun. Surrounding the core is the radiative zone, which extends from about 25% to about 70% of the Sun's radius. In this region, energy is transported primarily through radiation. The gamma rays produced in the core are absorbed by particles in the radiative zone and then re-emitted, often at slightly lower energies. Over countless absorptions and emissions, the high-energy gamma rays gradually lose energy and shift toward longer wavelengths, becoming X-rays and ultraviolet light. The radiative zone is incredibly dense, even more so than the densest materials on Earth. The plasma here is tightly packed, and energy moves through it very slowly, step by step, photon by photon. The temperature in the radiative zone decreases gradually as you move outward, from about 7 million degrees Celsius near the core to about 2 million degrees at the outer edge. Next comes the convective zone, which extends from about 70% of the Sun's radius to the surface. Here, the method of energy transport changes. The plasma is no longer dense enough or hot enough for radiation to be the dominant mode. Instead, energy is carried by convection, the same process that makes water boil in a pot or causes air to rise on a hot day. In the convective zone, hot plasma rises toward the surface, carrying energy with it. When it reaches the surface, it cools and radiates its energy into space. The cooled plasma then sinks back down, where it heats up again and rises once more. This creates vast circulation patterns, convection cells that churn and roil throughout the outer layers of the Sun. These convection cells are visible on the Sun's surface as granulation, a pattern that looks like a pot of boiling water when viewed through a telescope. Each granule is a convection cell, a rising column of hot plasma surrounded by darker lanes of cooler, sinking plasma. The granules are enormous, each one about 1,000 kilometers across, roughly the size of Texas. They form, expand, and dissolve in a matter of minutes, a constant churning motion that covers the entire surface of the Sun. Above the convective zone lies the photosphere, the visible surface of the Sun. This is the layer from which sunlight escapes into space. When you look at the Sun, you're seeing the photosphere. It's only about 500 kilometers thick, a thin shell compared to the Sun's total radius of nearly 700,000 kilometers. The photosphere is relatively cool compared to the interior of the Sun. Its temperature ranges from about 6,500 degrees Celsius at the base to about 4,000 degrees at the top. This makes it cool enough for some molecules to exist, though most of the plasma is still ionized. The photosphere appears bright and sharp-edged because it's the layer where the Sun's plasma becomes opaque to visible light. Below the photosphere, photons are constantly absorbed and re-emitted. Above it, they can escape freely into space. Sunspots appear on the photosphere. These are regions where strong magnetic fields suppress convection, causing the surface to cool slightly. Sunspots appear dark, not because they're truly dark, but because they're cooler than their surroundings, about 3,800 degrees Celsius compared to the surrounding 5,500 degrees. A sunspot, if removed from the Sun and placed in the night sky, would actually be quite bright. But against the brilliance of the surrounding photosphere, they appear as dark patches. Above the photosphere lies the chromosphere, a thin layer about 2,000 to 3,000 kilometers thick. The name comes from the Greek word chroma, meaning color, because the chromosphere emits a reddish glow during solar eclipses when the bright photosphere is blocked by the moon. This red color comes from hydrogen atoms emitting light at a specific wavelength. The chromosphere is puzzling. Unlike the interior of the Sun, where temperature decreases as you move outward, the chromosphere actually gets hotter the farther you go from the photosphere. At its base, the temperature is about 4,000 degrees Celsius, but at the top, it reaches about 20,000 degrees. Scientists aren't entirely sure why this happens, but it's thought to be related to energy carried by magnetic fields and shock waves rising from the convective zone below. The chromosphere is home to spicules, jets of gas that shoot upward from the surface at speeds of 20 to 30 kilometers per second. Spicules rise to heights of several thousand kilometers before falling back down. They appear as thin, hair-like structures sprouting from the Sun's surface, and they're constantly forming and disappearing, lasting only a few minutes each. Between the chromosphere and the corona lies a very thin region called the transition region, only about 100 kilometers thick. Here, the temperature rises abruptly, from about 20,000 degrees to about 1 million degrees over a very short distance. The transition region is difficult to observe because it's so thin and because the temperature changes so rapidly, but it's an important boundary between the cooler chromosphere and the extremely hot corona. The corona is the Sun's outermost layer, extending millions of kilometers into space. It's visible during total solar eclipses as a white halo around the Sun, with delicate streamers and loops of plasma stretching outward. The corona is incredibly hot, with temperatures reaching 2 million degrees Celsius or more. This is one of the great mysteries of solar physics. How can the corona be so much hotter than the photosphere below it? The answer likely lies in the Sun's magnetic field. Magnetic loops and arches thread through the corona, carrying energy from the surface. When these magnetic fields reconnect and release their energy, they can heat the surrounding plasma to extreme temperatures. But the exact mechanisms are still not fully understood, and this remains an active area of research. The corona is not static. It's constantly changing, shaped by the Sun's magnetic field. Coronal loops, arcs of plasma following magnetic field lines, rise and fall. Coronal holes, regions where the magnetic field opens up and allows plasma to escape, appear as dark patches in images of the corona. And occasionally, the corona erupts in powerful events called coronal mass ejections, hurling billions of tons of plasma into space. The Sun's structure is a marvel of physics and fluid dynamics, a complex layered system where energy is generated, transported, and finally radiated into space. Each layer plays its role, and together they create the star that lights our sky and warms our world. Nuclear fusion, the Sun's beating heart. At the heart of the Sun, Deep within its core, something extraordinary happens every second of every day. 4 hydrogen nuclei, simple protons, come together through a series of reactions to form one helium nucleus. In the process, a tiny fraction of their mass is converted into energy, and this energy is what powers the sun. This is nuclear fusion, and it's the reason the sun shines. The fusion process in the sun is called the proton-proton chain. It begins when 2 protons collide. Protons are positively charged, and like charges repel each other, so getting 2 protons close enough to fuse requires overcoming this electrostatic repulsion. In the sun's core, the protons are moving at incredibly high speeds because of the extreme temperature, and occasionally 2 of them collide with enough energy to overcome the repulsion and get very close together. Even then, fusion doesn't happen easily. The strong nuclear force, which binds protons and neutrons together inside atomic nuclei, has a very short range. It only works when particles are almost touching. The chance of any 2 protons fusing is extremely small. In fact, on average, a proton in the sun's core waits about 9 billion years before it successfully fuses with another proton. That's almost twice the current age of the sun. But the sun's core contains an unimaginable number of protons, something like 10 to the power of 56. Even though the chance of fusion for any individual proton is tiny, with so many protons present, fusion happens constantly. About 9.2 times 10 to the 37th fusion reactions occur in the sun's core every second. That's 92 million trillion reactions every second. When 2 protons do fuse, something interesting happens. One of them transforms into a neutron through a process called beta plus decay, mediated by the weak nuclear force. A positron, the antimatter counterpart of an electron, and a neutrino are emitted. The positron quickly encounters an electron and the 2 annihilate, releasing 2 gamma-ray photons. The neutrino, which barely interacts with matter, escapes from the sun entirely, passing through the sun's mass as if it weren't there and shooting off into space. Billions of these neutrinos pass through your body every second, day and night, without you ever noticing. The remaining particles, a proton and a neutron bound together, form a deuterium nucleus. Deuterium is an isotope of hydrogen, with 1 proton and 1 neutron. This is the first step of the proton-proton chain, and it's the slowest, rate-limiting step of the entire process. The deuterium nucleus doesn't last long. Within about 1 second on average, it collides with another proton and fuses to form helium-3, an isotope of helium with 2 protons and 1 neutron. This reaction releases a gamma-ray photon. Helium-3 is stable, and it can exist in the sun's core for a relatively long time, about 400 years on average. Eventually, 2 helium-3 nuclei collide and fuse. They combine to form helium-4, the common isotope of helium with 2 protons and 2 neutrons, and 2 protons are released. These protons can then participate in new fusion reactions. This completes the proton-proton chain. Net result: 4 hydrogen nuclei go in, 1 helium nucleus comes out, and a small amount of mass is converted into energy. The amount of mass converted is small but significant. The total mass of 4 hydrogen nuclei is slightly more than the mass of 1 helium nucleus. The difference, about 0.7% of the original mass, is converted into energy according to Einstein's equation. For every kilogram of hydrogen fused into helium, about 7 grams are converted into energy. This might not sound like much, but multiplied by the sheer amount of fusion happening in the sun's core, it adds up to an enormous output. The sun converts about 600 million tons of hydrogen into helium every second. Of this, about 4 million tons are turned into energy. This energy is initially in the form of high-energy gamma-ray photons and the kinetic energy of the particles involved in the reactions. The total power output of the sun is about 3.8 times 10 to the 26th watts. To put this in perspective, this is equivalent to exploding 100 billion tons of dynamite every second. This energy output has remained remarkably stable for billions of years. The sun burns steadily because of a self-regulating mechanism. If the fusion rate increases, the core heats up and expands, which reduces the density and temperature slightly, causing the fusion rate to decrease. If the fusion rate decreases, the core cools and contracts, increasing the density and temperature and causing the fusion rate to increase. This balance between gravitational collapse and the outward pressure from fusion is what keeps the sun stable. The proton-proton chain is not the only way hydrogen can fuse into helium. In hotter, more massive stars, Another process called the CNO cycle dominates. The CNO cycle uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium. It's more efficient than the proton-proton chain but requires higher temperatures to proceed at a significant rate. In the Sun, the CNO cycle accounts for less than 2% of the total energy production. The proton-proton chain is the main engine. The energy released in the core doesn't leave the Sun immediately. As we've discussed, photons produced in the core are absorbed and re-emitted countless times as they make their way outward, a random walk that can take hundreds of thousands of years. By the time the energy reaches the surface and escapes as sunlight, it has been transformed from high-energy gamma rays into visible light and infrared radiation. The neutrinos, however, leave immediately. Because they interact so weakly with matter, they pass straight through the Sun without being absorbed. They reach Earth about 8 minutes after being created, carrying with them information about the conditions in the Sun's core. By detecting these neutrinos, scientists can study the fusion reactions happening deep inside the Sun, something that would otherwise be impossible. Neutrino detection is challenging. Because neutrinos interact so weakly, you need enormous detectors to catch even a few of them. Experiments like the Sudbury Neutrino Observatory and Super Kamiokande have succeeded in detecting solar neutrinos, confirming our understanding of fusion in the Sun's core and even helping to solve a long-standing puzzle known as the solar neutrino problem, which revealed that neutrinos can change from one type to another as they travel through space. The fusion of hydrogen into helium is what sustains the Sun. It's been happening for over 4.5 billion years, and it will continue for about another 5 billion years, until the hydrogen in the core is exhausted. When that happens, the Sun will change. But for now, the Sun burns steadily, a nuclear furnace at the heart of our solar system converting mass into light and warmth, making life on Earth possible. Solar activity, spots, flares, and storms. The Sun is not a calm, unchanging sphere of light. It's a dynamic, active star, with a surface that roils and churns, punctuated by dark spots, bright flares, and powerful eruptions. This activity is driven by the Sun's magnetic field, which is generated deep within its interior and extends far out into space. The most visible signs of solar activity are sunspots. These are dark patches that appear on the photosphere, ranging in size from a few hundred kilometers to tens of thousands of kilometers across. Sunspots were first observed by Galileo in the early 17th century, and they've been studied intensively ever since. Sunspots appear dark because they're cooler than the surrounding photosphere. While the normal photosphere has a temperature of about 5,500 degrees Celsius, sunspots are about 1,500 degrees cooler, around 3,800 degrees. They're cooler because they're regions where strong magnetic fields inhibit the convection that normally brings hot plasma to the surface. The magnetic field lines rise up through the sunspots, suppressing the flow of heat from below. A typical sunspot consists of a dark central region called the umbra, surrounded by a lighter region called the penumbra. The umbra is the coolest part, where the magnetic field is strongest. The penumbra shows a radial structure, with bright and dark filaments stretching outward from the umbra, indicating the complex flow of plasma along the magnetic field lines. Sunspots usually appear in pairs or groups, with each spot in a pair having opposite magnetic polarity. This is because they mark the places where magnetic field lines emerge from the Sun's interior and loop through the photosphere before diving back down. The magnetic field in sunspot regions can be thousands of times stronger than Earth's magnetic field. The number of sunspots visible on the Sun varies over time in a predictable pattern known as the solar cycle. The solar cycle has an average length of about 11 years, though individual cycles can be as short as 9 years or as long as 13 years. During solar minimum, there may be days or even weeks with no sunspots visible on the Sun's surface. During solar maximum, dozens of sunspots may be present at once, covering large areas of the photosphere. The solar cycle is really a magnetic cycle. Over the course of about 11 years, the Sun's magnetic field builds up, becomes complex and tangled, and then reorganizes itself. At solar maximum, the Sun's magnetic poles flip, with the north magnetic pole becoming the south and vice versa. After another 11 years, the poles flip back, completing a full magnetic cycle of 22 years, known as the Hale cycle. Why does the Sun have this cycle? The answer lies in the Sun's rotation. The Sun doesn't rotate as a solid body. different parts of it rotate at different speeds, a phenomenon called differential rotation. The equator rotates faster than the poles, completing a rotation in about 25 days, while the poles take about 35 days. This differential rotation twists and tangles the magnetic field lines that thread through the Sun's interior. Over time, these twisted field lines become buoyant and rise to the surface, punching through the photosphere and creating sunspots. The more twisted and complex the field becomes, the more sunspots appear. Eventually, the field becomes so tangled that it reorganizes itself, the poles flip, and the cycle begins anew. Solar flares are another dramatic manifestation of solar activity. A solar flare is a sudden, intense burst of radiation from the Sun's surface, typically originating near sunspot groups. Flares occur when magnetic field lines that are twisted and tangled suddenly snap and reconnect, releasing enormous amounts of energy in the process. The energy released in a large solar flare can be equivalent to millions of hydrogen bombs exploding simultaneously. This energy is released across the electromagnetic spectrum, from radio waves to gamma rays, with the most intense emission often in X-rays and ultraviolet light. Flares can last from a few minutes to several hours. Solar flares are classified by their X-ray brightness. The smallest flares, called A-class flares, are barely detectable. B-class and C-class flares are more noticeable, but still relatively minor. M-class flares are medium-sized and can cause brief radio blackouts at Earth's poles. X-class flares are the largest and most powerful, capable of causing widespread radio blackouts, damaging satellites, and even posing a radiation hazard to astronauts in space. When a solar flare erupts, it sends a blast of radiation toward Earth at the speed of light. This radiation reaches Earth in about 8 minutes, the same time it takes for sunlight to travel from the Sun to Earth. When the flares, radiation hits Earth's upper atmosphere, it can ionize the particles there, disrupting radio communications and GPS signals. But flares aren't the only danger. Often accompanying a flare is something even more dramatic, a coronal mass ejection, or CME. A CME is a massive bubble of plasma and magnetic field that's hurled into space when part of the Sun's corona erupts. CMEs can carry billions of tons of material and travel at speeds of hundreds of kilometers per second, sometimes exceeding 1,000 kilometers per second. If a CME is directed toward Earth, it can cause a geomagnetic storm when it arrives. The journey from the Sun to Earth takes anywhere from 1 to 3 days, depending on the CME's speed. When the CME slams into Earth's magnetic field, it compresses and disturbs it, causing the magnetic field to fluctuate wildly. These fluctuations can induce electric currents in power lines, potentially damaging transformers and causing blackouts. They can disrupt radio, communications, especially at high latitudes. They can cause satellites to malfunction or even be destroyed, and they can create stunning auroras, the northern and southern lights, as charged particles from the CME spiral along Earth's magnetic field lines and collide with atoms in the upper atmosphere, causing them to glow. The strongest geomagnetic storm in recorded history was the Carrington event of 1859, named after the astronomer Richard Carrington, who observed the massive solar flare that triggered it. Telegraph systems around the world failed, and auroras were seen as far south as the Caribbean. If a similar event happened today, it could cause trillions of dollars in damage to our technology-dependent society. Solar activity also produces solar prominences, large loops or arcs of plasma that rise up from the Sun's surface and are suspended in the corona by magnetic fields. Prominences can be hundreds of thousands of kilometers long and can last for weeks or even months. When viewed against the disk of the Sun, they appear as dark filaments. When seen at the edge of the Sun during an eclipse, they glow with a reddish light. Sometimes a prominence becomes unstable and erupts, often triggering a CME. The plasma in the prominence follows the magnetic field lines as they stretch and snap, creating graceful arcs and loops that are among the most beautiful sights in all of solar physics. The Sun also emits a constant stream of plasma called the solar wind. This wind flows outward from the Sun in all directions, filling the solar system with a thin but significant population of charged particles. The solar wind is stronger and faster during times of high solar activity, when coronal holes, regions of open magnetic field lines, appear on the Sun's surface. The solar wind carries the Sun's magnetic field with it, creating a vast magnetic bubble around the solar system called the heliosphere. This bubble extends far beyond the orbit of Pluto, creating a boundary where the solar wind meets the interstellar medium, the gas and dust that fills the space between stars. NASA's Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Solar activity affects Earth in many ways, some subtle, some dramatic. It influences our climate, though the extent of this influence is still debated. It affects our technology, our communications, our satellites. It creates beautiful auroras and dangerous radiation storms. Understanding solar activity, predicting when flares and CMEs will occur, and preparing for their effects is an important part of modern space weather forecasting. And the Sun's activity is not random. It follows the 11-year cycle, rising to a peak at solar maximum and falling to a minimum during solar minimum. We're currently in solar cycle 25, which began in 2019. Solar maximum is expected to occur around 2024 or 2025, though predicting the exact timing and strength of solar cycles remains challenging. As you drift towards sleep, imagine the Sun's surface, covered in dark sunspots, erupting with bright flares, hurling plasma into space. It's a star alive with activity, a dynamic, ever-changing presence at the heart of our solar system. The solar wind and magnetic fields. The Sun doesn't just emit light and heat, it also sends a constant stream of particles flowing outward in all directions, a supersonic wind of plasma that fills the solar system. This is the solar wind, and it's one of the ways the Sun reaches across space and touches the planets, including Earth. The solar wind originates in the Sun's corona. The corona, as we've learned, is extremely hot, with temperatures of 1 to 2 million degrees Celsius or more. At these temperatures, the plasma in the corona has so much energy that it can escape the Sun's gravitational pull. The particles stream outward, accelerating as they go, reaching speeds of 300 to 700 kilometers per second by the time they reach Earth's orbit. The solar wind is made mostly of electrons and protons, with small amounts of heavier ions like helium, oxygen and iron. It's not very dense, about 5 particles per cubic centimeter near Earth, which is far less than the best vacuum we can create in a laboratory. Yet there are enough particles that they can carry energy and momentum, and they can interact with magnetic fields and atmospheres of planets. The solar wind is not uniform. It's divided into 2 main types, the slow solar wind and the fast solar wind. The slow solar wind moves at about 300 kilometers per second and comes from the equatorial regions of the Sun, where the magnetic field is more complex and closed. The fast solar wind, moving at 600 to 700 kilometers per second or more, comes from coronal holes, regions where the Sun's magnetic field opens up and allows plasma to escape more easily. The boundary between the slow and fast wind is not sharp. The 2 streams interact as they flow outward, creating turbulence and shock waves. When a fast stream overtakes a slow stream, it compresses the plasma ahead of it, creating a region of higher density and magnetic field strength. These interaction regions can affect space weather near Earth, sometimes triggering minor geomagnetic storms even without a CME. The solar wind carries with it the Sun's magnetic field. This field, frozen into the plasma, is carried outward from the Sun like strands of spaghetti spiraling away from a rotating nozzle. The combination of the Sun's rotation and the outward flow of the solar wind creates a spiral pattern in the magnetic field called the Parker spiral, named after Eugene Parker, the physicist who first predicted the solar wind's existence in 1958. Near Earth, the Sun's magnetic field in the solar wind is relatively weak, only a few nanoteslas compared to Earth's magnetic field of about 50,000 nanoteslas at the surface. But it's enough to have significant effects, especially when the field is oriented in a direction that allows it to merge with Earth's magnetic field. When the solar wind reaches Earth, it encounters the magnetosphere, the region of space dominated by Earth's magnetic field. The magnetosphere acts as a shield, deflecting most of the solar wind around the planet. The boundary between the solar wind and the magnetosphere is called the magnetopause, and it lies about 60,000 kilometers above Earth's equator on the sunward side. The pressure from the solar wind compresses the magnetosphere on the side facing the Sun and stretches it into a long tail on the night side, extending millions of kilometers into space. This magnetotail stores energy from the solar wind, and when this energy is released, it can create geomagnetic storms and auroras. The interaction between the solar wind and Earth's magnetosphere is complex and dynamic. When the magnetic field in the solar wind is oriented opposite to Earth's field, a process called magnetic reconnection can occur. The field lines from the Sun and Earth connect, allowing energy and particles to flow from the solar wind into the magnetosphere. This is one of the main ways energy from the Sun enters Earth's magnetic environment. The charged particles from the solar wind that enter the magnetosphere are funneled along Earth's magnetic field lines toward the poles. When they collide with atoms and molecules in the upper atmosphere, they cause those particles to emit light, creating auroras. The green glow of auroras comes from oxygen atoms at altitudes of about 100 to 300 kilometers. Red auroras, which are rarer, come from oxygen at higher altitudes. Blue and purple auroras come from nitrogen. Auroras are most common near the magnetic poles, where the field lines converge, but during strong geomagnetic storms they can be seen at much lower latitudes. The Carrington event of 1859 produced auroras visible in the Caribbean and Hawaii. More recently, strong geomagnetic storms in March 1989 and October 2003 brought auroras as far south as Texas and the Mediterranean. The solar wind doesn't just affect Earth. It interacts with all the planets in the solar system, each in different ways depending on whether the planet has a magnetic field and atmosphere. Mars, which has only a weak patchy magnetic field and a thin atmosphere, is directly exposed to the solar wind. Over billions of years, the solar wind has stripped away much of Mars' atmosphere, leaving the planet cold and dry. Venus has no magnetic field, but its thick atmosphere creates a barrier that the solar wind flows around. The solar wind interacts with the upper atmosphere of Venus, creating a magnetic tail similar to Earth's magnetotail, but induced by the planet's ionosphere rather than an intrinsic magnetic field. Jupiter has a powerful magnetic field, much stronger than Earth's, and a vast magnetosphere. The solar wind compresses Jupiter's magnetosphere on the sunward side but is unable to penetrate it. The giant planet's moons, particularly Io, contribute their own material to Jupiter's magnetosphere, creating intense radiation belts. Beyond the orbit of Pluto, the solar wind continues to flow outward until it reaches a boundary called the heliopause, where the pressure from the solar wind balances the pressure from the interstellar medium. This is the edge of the heliosphere, the Sun's sphere of influence. The Voyager 1 spacecraft crossed the heliopause in August 2012 at a distance of about 121 astronomical units from the Sun, roughly 18 billion kilometers. Voyager 2 followed in November 2018. The solar wind and the Sun's magnetic field are not just curiosities, they shape the environment of the entire solar system, creating the heliosphere that shields us from some of the galactic cosmic rays that would otherwise bombard the planets. They affect the atmospheres and surfaces of planets and moons. They create beautiful auroras and dangerous space weather. Understanding the solar wind and its interactions with the planets is crucial for exploring space and protecting our technology. And the solar wind is ancient. It's been flowing from the Sun for billions of years, ever since the Sun ignited fusion in its core and became a true star. It will continue to flow for billions of years more, until the Sun exhausts its fuel and begins its transformation into a red giant. For now, the solar wind streams steadily outward, a constant breath from the Sun, filling the space around us with its invisible presence. The Sun's influence on Earth and life. Every morning, the Sun rises and light floods across the land. This simple daily event is the foundation of almost everything that happens on Earth. Without the Sun's energy, our planet would be a frozen ball of ice with temperatures far below the freezing point of water. There would be no liquid water, no atmosphere as we know it, no plants, no animals, no life. The Sun provides Earth with energy in the form of light and heat. About 1,361 watts of solar energy strike each square meter of Earth's surface when the Sun is directly overhead, a value called the solar constant. Not all of this energy reaches the ground. Some is reflected back into space by clouds and ice, and some is absorbed by the atmosphere. But enough gets through to warm the planet and drive the processes that make Earth habitable. The energy from the Sun powers the water cycle. Solar radiation heats the oceans, causing water to evaporate and rise into the atmosphere as water vapor. The water vapor condenses into clouds, and the clouds release their moisture as rain or snow. The water flows back to the oceans through rivers and streams, and the cycle begins again, This cycle distributes fresh water across the planet, making it available for plants, animals, and humans. The sun also drives the circulation of the atmosphere. Solar heating is strongest at the equator, where the sun's rays strike most directly. The warm air at the equator rises, creating a region of low pressure. This rising air moves toward the poles at high altitudes, where it cools and sinks, creating regions of high pressure. The cool air then flows back toward the equator near the surface, completing a circulation pattern. This circulation, combined with Earth's rotation, creates the prevailing winds that shape our weather and climate. The sun's energy is captured directly by plants through photosynthesis, one of the most important chemical processes on Earth, and one of the most elegant solutions to the problem of how to harness energy from sunlight. In this remarkable biochemical pathway, plants use light energy from the sun to convert carbon dioxide from the atmosphere and water from the soil into sugars, specifically glucose, while releasing oxygen as a byproduct. The sugars provide energy and building blocks for the plant to grow, building complex molecules like cellulose for structure and starch for energy storage. The oxygen released into the atmosphere is what animals, including humans, breathe. Without photosynthesis, without plants capturing the sun's energy and producing oxygen as a waste product, complex life as we know it couldn't exist on Earth. The chemistry of photosynthesis is intricate and beautiful. It happens primarily in specialized structures called chloroplasts, found in the cells of leaves and other green parts of plants. Inside, chloroplasts are stacks of membrane-bound structures called thylakoids, where chlorophyll and other pigments capture photons of light. When a photon strikes a chlorophyll molecule, it excites an electron, boosting it to a higher energy level. This excited electron then begins a journey through a series of proteins and molecules in what's called the electron transport chain, gradually releasing its energy in controlled steps. This energy is used to pump protons across a membrane, creating a concentration gradient, and when those protons flow back through a special enzyme called ATP synthase, they generate ATP, the universal energy currency of life. Meanwhile, other reactions use the energy to split water molecules, releasing oxygen and providing electrons to replace those boosted by the light. The released oxygen molecule, two oxygen atoms bound together as O2, drifts out of the leaf through tiny pores called stomata and enters the atmosphere. Over billions of years, photosynthesis has transformed Earth's atmosphere. Early in Earth's history, the atmosphere contained little free oxygen. It was dominated by nitrogen, carbon dioxide, water vapor, and other gases. But as photosynthetic organisms evolved, first single-celled cyanobacteria about 2.5 billion years ago, then later algae, and land plants, they began pumping oxygen into the atmosphere. This great oxygenation event, as it's called, fundamentally changed our planet, making it possible for complex multicellular life to evolve. The oxygen we breathe today is the accumulated product of billions of years of photosynthesis, countless trillions of plants and algae capturing sunlight and releasing oxygen, slowly transforming our world. Photosynthesis is also the foundation of virtually all food chains and food webs on Earth. When you think about it, almost every bit of food you've ever eaten can be traced back to photosynthesis, to some plant somewhere capturing the sun's energy. If you eat a salad, you're directly eating the products of photosynthesis, the leaves and fruits and roots that plants built using energy from sunlight. If you eat meat, you're eating an animal that ate plants, or that ate other animals that ate plants. Even fish in the ocean ultimately depend on phytoplankton, tiny photosynthetic organisms floating in the water, capturing sunlight filtering down through the waves. There are a few exceptions, like the ecosystems around deep-sea hydrothermal vents, where bacteria use chemical energy from volcanic activity rather than sunlight, but these are rare and limited. The vast majority of life on Earth, probably more than 99% of all biomass, depends directly or indirectly on photosynthesis. When you eat breakfast, lunch, or dinner, you're consuming solar energy that was captured by plants, converted into chemical form, and stored in the bonds of sugar and starch and protein molecules. In a very real sense, we are all solar-powered. The energy that allows your heart to beat, your brain to think, your muscles to move, all of it originally came from the sun, captured by plants, transferred through the food chain, and now powering your body. The sun's influence on life doesn't stop at providing energy. Sunlight also regulates the rhythms of life on Earth, the daily and seasonal cycles that govern so much of biology. Many organisms, from single-celled algae to complex animals like humans, have internal biological clocks, circadian rhythms that cycle with a period of roughly 24 hours. These rhythms evolved to match the day-night cycle created by Earth's rotation and the sun's daily passage across the sky. Your body's circadian rhythm affects when you feel sleepy, and when you feel alert, when you're hungry, when certain hormones are released, even how your body temperature fluctuates throughout the day. The primary signal that keeps your circadian rhythm synchronized with the external world is light, specifically sunlight hitting photoreceptors in your eyes. This is why exposure to bright light in the morning helps you wake up and feel alert, and why dimming the lights in the evening helps prepare your body for sleep. Seasonal changes, too, are driven by the sun, though in a more indirect way. Earth's axis of rotation is tilted by about 23.5 degrees relative to the plane of its orbit around the sun. This tilt means that during part of the year, the northern hemisphere is angled toward the sun, receiving more direct sunlight and experiencing longer days. This is summer in the northern hemisphere. 6 months later, the northern hemisphere is angled away from the sun, receiving less direct sunlight and experiencing shorter days. This is winter in the northern hemisphere. The southern hemisphere experiences the opposite pattern, summer when the north has winter and vice versa. This annual cycle of seasons, this rhythmic change in the amount and angle of sunlight, profoundly affects life. Trees lose their leaves in autumn and grow new ones in spring. Plants flower at specific times of year, often triggered by changes in day length. Animals time their reproduction to when food will be most available. Birds throughout human history, people have been deeply aware of the sun's power and importance. It's no accident that so many ancient cultures worshipped the sun as a god or primary deity. When you depend directly on agriculture, when you don't have electric lights or central heating, when the changing seasons determine whether you'll have enough food to survive the winter, the sun's significance is impossible to ignore. It's literally a matter of life and death. Ancient Egypt built one of history's greatest civilizations in large part because of the reliable flooding of the Nile River, which was driven by seasonal rains in the Ethiopian highlands, which were themselves part of seasonal patterns controlled by the sun. The Egyptians worshipped Ra, the sun god, who they believed sailed across the sky each day in a boat, traveling through the underworld each night to be reborn at dawn. Pharaohs were considered the sons of Ra, divine rulers whose authority flowed from the sun itself. The pyramids, those massive monuments that still stand after 4,500 years, were aligned with incredible precision to the cardinal directions, and many scholars believe they had symbolic connections to the sun's journey across the sky. In Mesoamerica, the Maya and Aztec civilizations developed sophisticated astronomical observations and calendars based on careful tracking of the sun's movements through the year. The Maya built temples and cities with structures aligned to mark solstices and equinoxes, the days when the sun reaches its highest and lowest points in the sky, or when day and night are equal in length. The Aztecs believed the sun god Tonatiuh needed to be sustained with human sacrifice, that he required human blood to have the strength to rise each day and complete his journey across the sky. While we now know this belief was mistaken, it shows just how vital and powerful the sun was in their world view, important enough to demand the most valuable offering they could give. In ancient Greece, Helios drove his golden chariot across the sky each day, pulled by 4 immortal horses. Apollo, another solar deity, represented light, truth, music, and prophecy. The Greeks understood that the sun was essential to life and prosperity, even if they didn't understand the physical mechanisms of how it worked. In ancient China, legends spoke of 10 suns that once filled the sky, burning everything, until the archer Hou Yi shot down 9 of them with his bow, leaving just one to light the world. Japan reveres Amaterasu, the sun goddess, whose importance is reflected in the Japanese flag, the red circle representing the rising sun. Indigenous peoples around the world developed their own solar myths, rituals, and observations. The Inca of South America worshipped Inti, the sun god, and built Machu Picchu and other sites with careful solar alignments. The Inti, the sun's influence on life doesn't stop there. Sunlight regulates the rhythms of life on Earth. Many organisms, from single-celled algae to humans, have internal clocks that are synchronized to the 24-hour cycle of day and night. These circadian rhythms control sleep and wakefulness, feeding patterns, hormone production, and many other biological processes. The sun's daily appearance and disappearance is the primary signal that keeps these rhythms aligned with the environment. Seasonal changes are also driven by the sun. Earth's axis is tilted by about 23.5 degrees relative to its orbit around the sun. This tilt means that during part of the year, the northern hemisphere is tilted toward the sun, receiving more direct sunlight and experiencing summer. 6 months later, the northern hemisphere is tilted away from the sun, receiving less direct sunlight and experiencing winter. The southern hemisphere experiences the opposite pattern. These seasonal changes affect everything from temperature and daylight hours to plant growth and animal behavior. Trees lose their leaves in autumn, plants flower in spring, birds migrate to follow food sources, and animals hibernate or adapt to survive the cold. The cycle of seasons, driven by Earth's tilt and its orbit around the sun, is one of the fundamental rhythms of life on this planet. Historically, the sun has also influenced human civilizations. Ancient peoples built structures aligned with the sun's path across the sky. Stonehenge in England, the pyramids of Egypt, and the temples of the Maya all incorporate solar alignments, marking solstices, equinoxes, or other important dates in the solar calendar. These alignments show the importance of the sun in ancient religions and cultures, as well as the sophisticated astronomical knowledge these civilizations possessed. In more recent times, humans have learned to harness the sun's energy directly. Solar panels convert sunlight into electricity, providing a clean, renewable source of power. Solar water heaters use sunlight to heat water for homes and businesses, and passive solar design uses the sun's warmth to heat buildings in winter, while minimizing heat gain in summer. The sun's influence on Earth extends beyond the energy it provides. The sun's gravity keeps Earth in its orbit, preventing us from drifting off into interstellar space. The stability of the sun's energy output over billions of years has allowed life to evolve and flourish. If the sun's output varied wildly, as some stars do, Earth's climate would be chaotic, and complex life might never have developed. But the sun's influence is not always benign. As we've learned, solar flares and coronal mass ejections can disrupt technology, damage satellites, and pose risks to astronauts. Strong geomagnetic storms can cause power outages, as happened in Quebec in March 1989 when a CME knocked out the power grid for 9 hours, affecting 6 million people. The sun's ultraviolet radiation is both beneficial and harmful. Small amounts of UV exposure help our bodies produce vitamin D, which is essential for healthy bones, but too much UV exposure can damage skin cells and cause skin cancer. Earth's ozone layer, a region of the stratosphere where ozone molecules are concentrated, absorbs most of the sun's harmful UV radiation, protecting life on the surface. Human activities, particularly the release of chlorofluorocarbons, damaged the ozone layer in the late 20th century, but international efforts to phase out these chemicals have allowed the ozone layer to begin recovering. The sun has also shaped Earth's history in more dramatic ways. Long-term variations in Earth's orbit and axial tilt, known as Milankovitch cycles, have influenced Earth's climate over tens of thousands of years, contributing to the ice ages. While these cycles don't change the total amount of solar energy Earth receives, they do change how that energy is distributed across the planet and throughout the year, and this is enough to trigger major climate shifts, and the sun will continue to influence Earth's future. As the sun ages and its core gradually converts more hydrogen into helium, the sun's energy output is slowly increasing. Over the next billion years or so, the sun will become about 10% brighter. This may not sound like much, but it will be enough to have profound effects on Earth's climate. As the sun brightens, Earth will warm, causing more water to evaporate from the oceans and increasing the greenhouse effect. Eventually, Earth may become too hot for liquid water to exist on the surface, ending the habitability of our planet. But that's a long way in the future. For now, the sun shines steadily, providing the energy that makes our world a living, breathing planet, a place of forests and oceans, of birds and bees, of cities and civilizations. As you drift towards sleep, think of the sun hanging in space, 93 million miles away, pouring out its light and warmth, sustaining all the life on Earth. The sun's future journey. The sun seems eternal, unchanging, a constant presence in the sky. But like all stars, the Sun has a life cycle. It was born, it's living now in its prime, and one day, billions of years in the future, it will die. The Sun's future is already written in the laws of physics, and astronomers can predict with reasonable accuracy what will happen. Right now, the Sun is about 4.6 billion years old. It's about halfway through its main sequence phase, the long period of stable hydrogen burning in its core. The Sun has been fusing hydrogen into helium for all this time, gradually converting its core into helium ash. About half the hydrogen in the core has been used up. The other half will last for roughly another 5 billion years. During this time, the Sun will continue much as it is now, but with one important change: it will slowly get brighter. As helium accumulates in the core, the density and temperature increase slightly, causing the fusion reactions to proceed a bit faster. This means the Sun's energy output increases. Over the past 4.5 billion years, the Sun has become about 30% brighter than it was when it first ignited fusion. Over the next billion years, it will become another 10% brighter still. This brightening will have consequences for Earth. As the Sun's output increases, Earth will warm. The oceans will evaporate more quickly, increasing the amount of water vapor in the atmosphere. Water vapor is a greenhouse gas, so this will cause further warming in a runaway feedback loop. Eventually, perhaps a billion years from now, Earth's oceans will boil away and the planet will become a hot, lifeless desert, similar to Venus today. But the Sun's transformation will be far more dramatic. In about 5 billion years, the hydrogen in the Sun's core will finally be exhausted. When this happens, fusion in the core will stop. Without the outward pressure from fusion to balance gravity, the core will begin to collapse. As the core collapses, it will heat up. The temperature will rise high enough that the hydrogen in a shell around the core will start fusing into helium. This is called hydrogen shell burning. The energy from this shell burning will be even greater than the energy the Sun produced during its main sequence phase. The Sun will become brighter and larger. The outer layers of the Sun, heated by the energy from the shell, will expand enormously. The Sun will swell into a red giant, growing to perhaps 100 times its current size. Its surface will cool, giving it a reddish colour even though it's actually producing more energy than ever before. The Sun's radius will extend past the orbit of Mercury, possibly past Venus, and might even reach Earth's orbit. If Earth is engulfed by the Sun's expanding envelope, it will be vaporized. But even if Earth's orbit lies just outside the Sun's surface, the intense heat will make the planet uninhabitable. The atmosphere will be stripped away, the oceans will have long since boiled off, and the surface will melt. Earth, if it survives at all, will become a scorched, lifeless rock. The Sun will spend about 1 billion years as a red giant. During this time, the core will continue to contract and heat up. Eventually, the core temperature will reach about 100 million degrees Celsius, hot enough for helium nuclei to fuse into carbon through a process called the triple alpha process. 3 helium nuclei combine to form carbon-12, releasing energy in the process. This helium fusion will ignite suddenly in an event called a helium flash, releasing a huge burst of energy. But because the core is so dense, this energy is absorbed by the star's outer layers rather than being radiated away, so the helium flash is not visible from the outside. Once helium fusion begins, the Sun will settle into a new, temporary equilibrium, fusing helium in the core and hydrogen in a shell around the core. This phase will last only about 100 million years, a short time compared to the billions of years the Sun spent on the main sequence. When the helium in the core is exhausted, the core will once again collapse and heat up. Now the Sun will have 2 shells of fusion, an inner shell fusing helium into carbon and an outer shell fusing hydrogen into helium. The energy output will be enormous, and the Sun will swell even larger, becoming an asymptotic giant branch star. But the Sun's outer layers are only weakly bound to the core at this point. The intense energy from the core will push the outer layers outward, and the Sun will begin to lose mass. Strong stellar winds will blow off the outer envelope, carrying away gas and dust. The Sun will shed its outer layers in pulses, expelling material into space. These expelled layers will form a beautiful planetary nebula, a glowing shell of gas expanding away from the dying star. The name is misleading. Planetary nebulae have nothing to do with planets. They were named by early astronomers who thought they looked like planets through their telescopes. Today we know they're the cast-off envelopes of dying stars. Famous examples include the Ring Nebula, the Helix Nebula, and the Cat's Eye Nebula. At the centre of the planetary nebula, the Sun's core will remain. This core, now made mostly of carbon and oxygen, will no longer have the temperature or pressure needed to fuse these elements. Fusion will cease entirely. The core will have become a white dwarf, an incredibly dense object about the size of Earth, but containing about half the Sun's original mass. A teaspoon of white dwarf material would weigh several tons. White dwarfs don't generate energy through fusion. They shine only because they're hot, radiating away the leftover thermal energy from their past. Initially, the white dwarf that was once the Sun will have a surface temperature of over 100,000 degrees Celsius, hot enough to emit ultraviolet light. This UV radiation will illuminate the surrounding planetary nebula, making it glow in a variety of colours as different atoms absorb and re-emit the light. But over billions of years, the white dwarf will cool. With no source of new energy, it will slowly radiate away its heat. Its colour will shift from blue-white to yellow to red as it cools. Eventually, after trillions of years, far longer than the current age of the universe, the white dwarf will become too cool to emit any visible light. It will become a black dwarf, a cold, dark cinder drifting through space. The planetary nebula, meanwhile, will expand and disperse. After 10,000 years or so, it will be spread so thin that it's no longer visible. The gas and dust from the Sun's former envelope will mix with the interstellar medium, perhaps one day becoming part of a new generation of stars and planets. This is the fate that awaits the Sun. Not a violent explosion, not a catastrophic collapse, but a gradual fading, a slow transformation from a bright, life-giving star to a dim ember. It's a peaceful end, and in some ways, a fitting one for a star that has shone so steadily for billions of years. The planets of the solar system will fare differently. Mercury and Venus will almost certainly be engulfed and destroyed when the Sun becomes a red giant. Earth's fate is uncertain. It might survive in a wider orbit, or it might be consumed. Mars will likely survive, though it will be a scorched and airless world. The gas giants, Jupiter, Saturn, Uranus, and Neptune, will probably survive largely intact, though their orbits may shift outward as the Sun loses mass. The moons of the outer planets might experience a brief, ironic bloom. As the Sun brightens during its red giant phase, these distant worlds will receive more energy. Ice on moons like Europa, Enceladus, and Titan might melt, creating liquid water oceans. For a short time, perhaps a few million years, these moons might become habitable, warmed by the dying Sun. But this would be a fleeting moment, and as the Sun fades to a white dwarf, these worlds would freeze again. The Sun's death is billions of years away, so far in the future that humanity, if it still exists, will be unrecognisably different. We have plenty of time. Perhaps we will have spread to other star systems by then, leaving the solar system behind. Perhaps we will have found ways to survive, or even to move Earth to a safer orbit. Or perhaps, by then, humanity will have evolved into something entirely new, something we cannot even imagine today. But for now, the Sun is alive and well, burning steadily in the sky, and it will continue to do so for a very long time. Humanity's dance with the Sun. For all of human history, the Sun has been more than just a star in the sky. It's been a god, a symbol, a source of wonder and inspiration. Ancient cultures around the world revered the Sun, building monuments to track its movements and creating myths to explain its daily journey across the sky. The ancient Egyptians worshipped Ra, the sun god, who travelled across the sky in a boat each day and journeyed through the underworld each night. Pharaohs were seen as the sons of Ra, divine rulers whose authority came from the sun itself. The massive pyramids were aligned with astronomical precision, and many temples were oriented to capture the sun's rays on important dates. In Mesoamerica, the Aztecs believed the sun needed to be fed with human sacrifice to continue its journey across the sky. The sun god Tonatiuh demanded blood to give him strength. While we now know this belief was unfounded, it shows the immense importance the sun held in their worldview. The Maya, too, closely tracked the sun's movements, developing an accurate calendar based on its annual journey. In ancient Greece, Helios drove his chariot across the sky each day, pulled by 4 magnificent horses. Apollo, another solar deity, represented light, music, and truth. These myths were ways of understanding and honouring the sun's power and constancy. In China, the sun was represented by a 3-legged crow called the Sanzhuwu. Legend spoke of 10 suns that once filled the sky, until the archer Hou Yi shot down 9 of them, leaving only one to light the world. Japanese mythology reveres Amaterasu, the sun goddess, whose importance is reflected in Japan's national flag, the rising sun. Indigenous peoples around the world developed their own solar myths and traditions. The Inca worshipped Inti, the sun god, and built the great city of Machu Picchu with structures aligned to solar events. In North America, many Native American tribes held sun dances and ceremonies to honor the sun's life-giving power. These myths and traditions weren't just superstition. They represented a deep awareness of humanity's dependence on the sun. Without understanding the science, ancient peoples recognized that the sun was essential to life, that its rhythms governed the seasons and the harvest, and that its presence or absence could mean the difference between abundance and famine. The scientific study of the sun began in earnest in the 17th century. Galileo's observations of sunspots in 1610 challenged the Aristotelian view that the heavens were perfect and unchanging. Over the following centuries, astronomers developed increasingly sophisticated instruments to study the sun. In 1814, Joseph von Fraunhofer discovered dark lines in the sun's spectrum, absorption lines caused by elements in the sun's atmosphere. These Fraunhofer lines allowed astronomers to determine the sun's chemical composition. In 1868, during a solar eclipse, astronomers observed a yellow spectral line that didn't match any known element. They concluded it came from a new element, which they named helium after the Greek word for sun, helios. Helium wasn't discovered on Earth until 1895. The 20th century brought revolutionary advances in our understanding of the sun. In 1920, Arthur Eddington suggested that the sun might be powered by nuclear fusion, though the details weren't worked out until the 1930s and 40s. Hans Bethe's work on the proton-proton chain earned him the Nobel Prize in Physics in 1967. The space age allowed us to study the sun in ways that were impossible from Earth's surface. Satellites and space probes equipped with instruments that could detect ultraviolet light, X-rays and particles gave us new views of the sun's corona, its magnetic field and its activity. Missions like Skylab, the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and the Parker Solar Probe have transformed our understanding of how the sun works. The Parker Solar Probe, launched in 2018, is designed to fly closer to the sun than any spacecraft before it, passing through the corona and directly sampling the solar wind. It's named after Eugene Parker, the physicist who predicted the existence of the solar wind in 1958. At its closest approach, the Parker Solar Probe will come within about 6 million kilometers of the sun's surface, traveling at speeds of up to 700,000 kilometers per hour. It will experience temperatures of over 1,000 to 400 degrees Celsius, protected by a cutting-edge heat shield. Today, studying the sun is not just about satisfying curiosity, it has practical importance. Space weather forecasting helps protect satellites, power grids, and astronauts from the effects of solar flares and coronal mass ejections. Understanding the sun's variability helps us understand Earth's climate and predict how it might change in the future. And studying the sun helps us understand other stars, since the sun is the only star we can observe in such detail. Humans have also learned to harness the sun's energy. Solar panels, or photovoltaic cells, convert sunlight directly into electricity using semiconductors. When light strikes the cell, it knocks electrons loose, creating an electric current. Solar panels have become increasingly efficient and affordable, and they're now a major source of renewable energy. In 2023, solar power accounted for a growing percentage of global electricity generation, and this percentage continues to increase. Solar thermal energy, which uses the sun's heat rather than its light, is used for a variety of purposes. Solar water heaters use sunlight to heat water for homes and businesses. Concentrated solar power plants use mirrors to focus sunlight onto a central receiver, heating a fluid that drives a turbine to generate electricity. Even passive solar design, which uses the sun's warmth without any mechanical or electrical devices, can significantly reduce energy use in buildings. Properly oriented windows, thermal mass to store heat, and overhangs to shade windows in summer while allowing sunlight in winter can make buildings much more energy efficient. As we face the challenge of climate change, the sun offers a clean, abundant source of energy. Unlike fossil fuels, which release carbon dioxide and contribute to global warming, Solar energy produces no greenhouse gases. The sun delivers more energy to Earth in 1 hour than humanity uses in an entire year. The challenge is capturing and storing that energy efficiently and affordably. The sun also continues to inspire us. Solar eclipses, rare events when the moon passes directly between Earth and the sun, briefly blocking the sun's light, are still occasions of wonder. During a total solar eclipse, the sky darkens, the temperature drops, and the sun's corona becomes visible as a glowing halo. People travel thousands of miles to witness a total eclipse, standing in the path of totality to experience the otherworldly sight of the sun being blotted out. The sun appears in our art, our literature, our music. Vincent van Gogh's paintings captured the sun's light in vivid yellows and golds. Poets from ancient times to the present have written about the sun, using it as a symbol of hope, enlightenment, and life. The sun is a universal symbol, recognized and revered by cultures around the world, and as we look to the future, the sun will continue to be central to our existence. If humanity spreads to other planets and star systems, we'll carry with us the memory of our home star, the sun that nurtured life on Earth. Perhaps one day, far in the future, humans will witness the sun's transformation into a red giant from a safe distance, watching as the star that gave us life swells and changes, marking the end of an era. But for now, the sun rises each morning, a gentle giant warming our world, making life possible, and lighting our way. Closing thoughts. We've journeyed through the sun's story tonight, from its birth in a collapsing cloud of gas and dust, through its current life as a stable, hydrogen-burning star, to its far future as a red giant and white dwarf. We've explored its layers from the blazing core where fusion creates energy through the radiative and convective zones to the surface where that energy finally escapes as light. We've learned about its magnetic field, its spots and flares, its 11-year cycle of activity, and the solar wind that fills the space around us. We've seen how the sun influences Earth, powering the water cycle, driving the weather, enabling photosynthesis, and creating the conditions for life. We've looked at humanity's long relationship with the sun, from ancient myths to modern science, from solar worship to solar power. The sun is not just a ball of gas in the sky. It's the heart of our solar system, the source of almost all the energy on Earth, the reason life exists at all. It's been shining for 4.5 billion years, and it will shine for 4.5 billion more. By human standards, the sun is eternal. By cosmic standards, it's just one star among billions, ordinary in almost every way, except that it's ours. As you drift towards sleep, imagine the sun, hanging in space, 93 million miles away, a sphere of plasma held together by gravity, powered by fusion, radiating light in all directions. That light takes 8 minutes to reach us, travelling across the void at 300,000 kilometers per second. Some of that light is warming your skin right now, or it will be when morning comes. Some of it is feeding the plants that provide your oxygen. Some of it is evaporating water from the oceans, creating clouds that will bring rain. The sun is always there, always shining, always giving. It asks for nothing in return. It simply burns, steadily and patiently, as it has for billions of years, as it will for billions more, and for as long as it shines, it makes our world a place of warmth and light, of life and possibility. If this journey through the sun's story has helped you relax or given you something peaceful to think about as you fall asleep, consider liking this video and subscribing to the Dreamy Science channel. It helps others find these gentle explorations too. Rest well and dream softly. Good night. Watana, or Festival of the Sun, was their most important ceremony, marking the winter solstice in June in the southern hemisphere. In North America, many Native American tribes held sun dances and ceremonies. The Plains tribes performed elaborate sun dance rituals that could last for days, involving fasting, dancing, and prayers for renewal and thanks to the sun's life-giving power. Even Stonehenge, that mysterious circle of massive standing stones on the Salisbury Plain in England, shows sophisticated solar awareness. Built over several phases between about 3000 and 2000 BCE, Stonehenge is aligned so that on the summer solstice, the longest day of the year, the sun rises directly over the heel stone when viewed from the centre of the monument. Thousands of people gather at Stonehenge every year to watch this sunrise, a tradition connecting modern observers with the ancient, builders who arranged those enormous stones with such precision without the benefit of metal tools or wheeled vehicles, somehow transporting stones weighing dozens of tons and positioning them to mark the sun's journey through the seasons. These ancient observations weren't just spiritual or religious, they were practical. Understanding the sun's movements allowed ancient peoples to create calendars to predict the seasons, to know when to plant crops and when to harvest, when to expect floods or droughts. Agriculture depends on timing, on planting at the right season so crops mature when conditions are suitable, and ancient farmers who understood the solar calendar had a significant advantage. The development of accurate calendars based on solar observations was one of the fundamental achievements of early civilizations, essential for organizing agricultural societies. The scientific study of the sun in the modern sense really began in the 17th century with the invention of the telescope. In 1610, Galileo Galilei, using a relatively simple refracting telescope he'd built himself based on descriptions of Dutch inventions, turned his instrument toward the sun and discovered sunspots, dark patches on the sun's surface. This was revolutionary. According to the prevailing Aristotelian philosophy of the time, the heavens were supposed to be perfect and unchanging, made of a special fifth element different from the four earthly elements of earth, water, air, and fire. The sun as a celestial object should have been a perfect, unblemished sphere. But Galileo observed spots on the sun, imperfections, and moreover, these spots moved across the sun's face and changed over time, proving that the sun was not perfect and unchanging but dynamic and active. Galileo's observations were dangerous. He was already in trouble with the Catholic Church for his support of the Copernican heliocentric model, which placed the sun at the centre of the solar system rather than Earth. His telescopic observations of the phases of Venus, the moons of Jupiter, and now sunspots provided strong evidence for the Copernican model and against the Ptolemaic geocentric system favoured by the Church. Eventually, in 1633, Galileo was tried by the Roman Inquisition, found vehemently suspect of heresy, and forced to recant his views. He spent the rest of his life under house arrest. But his observations had been published and could not be suppressed. They mark the beginning of modern solar astronomy. Over the next few centuries, astronomers continued to observe the sun and make new discoveries. In 1814, Joseph von Fraunhofer discovered dark absorption lines in the solar spectrum, now called Fraunhofer lines. When sunlight is passed through a prism or diffraction grating, it spreads out into a rainbow of colours, a continuous spectrum. But overlaid on this spectrum are thousands of thin dark lines at specific wavelengths. These lines are caused by atoms in the sun's atmosphere absorbing light at characteristic wavelengths. Each element has its own unique pattern of absorption lines, like a fingerprint. By studying these lines, astronomers could determine what elements were present in the sun and in what quantities, even though the sun was millions of miles away and they couldn't collect a physical sample. This was the birth of astronomical spectroscopy, one of the most powerful tools in modern astronomy. In 1868, during a total solar eclipse, when the moon blocks the bright photosphere and allows observations of the sun's fainter outer layers, astronomers observed a bright yellow line in the spectrum that didn't match any element known on Earth at the time. They concluded this line must come from a new element, and they named it helium, from helios, the Greek word for sun. For decades, helium was known only from its presence in the sun's spectrum. It wasn't until 1895 that helium was finally discovered on Earth, isolated from uranium ore. Today we know helium is the second most abundant element in the universe after hydrogen, making up about 24% of normal matter by mass, and it's the product of hydrogen fusion in stars. But for 27 years, helium was known only from the sun, an element discovered in the sky before it was found on the ground. The sun's distance from Earth was another major question that took centuries to answer accurately. Ancient astronomers like Aristarchus of Samos tried to measure the sun's distance using geometric methods, but their estimates were far too small. In the 17th and 18th centuries, astronomers used transits of Venus, rare events when Venus passes directly between Earth and the Sun and appears as a small black dot crossing the solar disk, to triangulate the Sun's distance more accurately. Multiple observations from different points on Earth allowed them to use parallax, the apparent shift in Venus's position against the Sun's disk due to the different viewing angles, to calculate the Sun-Earth distance. These transit expeditions were major undertakings, with astronomers travelling to remote locations around the world, from Siberia to Tahiti, to make their observations. By the mid-19th century, they had determined that the Sun was about 93 million miles away, very close to the modern SEC-LM. But many fundamental questions about the Sun remained mysteries. How old was it? What made it shine? How could it have burned so steadily for so long? In the 19th century, scientists knew that chemical reactions like burning coal or wood couldn't possibly power the Sun for more than a few thousand years. The Sun simply emitted too much energy. Some proposed that the Sun was gradually shrinking under gravity, converting gravitational potential energy into heat and light, a process called Kelvin-Helmholtz contraction, after the physicists who studied it. This could power the Sun for perhaps 20 or 30 million years, long enough to satisfy Lord Kelvin's own incorrect calculations of Earth's age based on its rate of cooling. But as geologists studied rock layers and fossils, it became clear that Earth was much older than that, at least hundreds of millions of years old. And if Earth was that old, the Sun must be at least as old, probably older. So what could power it for so long? The answer came from nuclear physics, developed in the early 20th century. In 1920, Arthur Eddington proposed that the Sun might be powered by the fusion of hydrogen into helium, though he didn't know the specific reactions involved. If, indeed, the subatomic energy in the stars is being freely used to maintain their great furnaces, it seems to bring a little nearer to fulfillment our dream of controlling this latent power for the well-being of the human race, or for its suicide, he wrote presciently, decades before nuclear weapons and nuclear power became realities. In the 1930s, Hans Bethe and others worked out the details of nuclear fusion in stars, including the proton-proton chain that powers the Sun. Bethe's work was recognized with the Nobel Prize in Physics in 1967. Finally, scientists understood the source of the Sun's energy and could calculate how long it could shine. The answer, billions of years, more than enough to account for Earth's geological age and for the entire history of life. The space age, beginning in the 1950s, revolutionized solar astronomy. For the first time, scientists could place instruments above Earth's atmosphere, which blocks much of the electromagnetic spectrum, including most ultraviolet light, X-rays, and gamma rays. From space, telescopes could observe the Sun in wavelengths invisible from the ground, revealing new phenomena and providing unprecedented detail. Satellites like Skylab in the 1970s, the Solar and Heliospheric Observatory. Launched in 1995, the Solar Dynamics Observatory launched in 2010, and many others have monitored the Sun continuously, tracking its activity, studying its magnetic field, and helping us understand solar physics at a level impossible just a few decades ago. One of the most ambitious solar missions currently underway is the Parker Solar Probe, launched by NASA in August 2018. Named after Eugene Parker, the physicist who predicted the existence of the solar wind in 1958, making him the first living person to have a NASA spacecraft named after them. The Parker Solar Probe is designed to fly closer to the Sun than any previous mission. At its closest approach, it will come within about 6 million kilometers of the Sun's surface, skimming through the corona itself, directly sampling the solar wind and measuring the conditions in this extreme environment. To survive these close approaches, the Parker Solar Probe is equipped with a cutting-edge heat shield, a carbon composite shield about 11.5 centimeters thick. This shield can withstand temperatures exceeding 1,400 degrees Celsius, hot enough to melt many metals. Behind this shield, the spacecraft and its instruments remain at a relatively comfortable room temperature, protecting the sensitive electronics and scientific equipment. The probe will eventually complete 24 close approaches to the Sun, each orbit bringing it slightly closer, moving at speeds exceeding 700,000 kilometers per hour, making it the fastest human-made object ever built. The data it's collecting is helping answer long-standing questions about the Sun, particularly about the corona's extreme temperature and the acceleration of the solar wind. Understanding the Sun has become increasingly important in our modern technological society. We depend on satellites for communication, navigation, weather forecasting, and military surveillance. We depend on interconnected power grids that span continents. All of these systems are vulnerable to space weather, to the effects of solar flares and coronal mass ejections. A severe solar storm hitting Earth today could cause widespread blackouts, disable satellites, disrupt GPS navigation, interfere with radio communications, and potentially cause trillions of dollars in economic damage. This isn't hypothetical. It has happened before on smaller scales and could happen again on a larger scale. The Carrington event of 1859 remains the strongest geomagnetic storm on record. Telegraph systems around the world, the cutting-edge communication technology of the time, failed. Some telegraph operators reported receiving electric shocks from their equipment. Some telegraph systems continued to operate even after their power sources were disconnected, powered by the electrical currents induced in the telegraph wires by the magnetic storm. Auroras were visible as far south as the Caribbean and Hawaii, brilliant displays of red, green and purple light filling the night sky in places where auroras are normally never seen. If a Carrington-scale event happened today, the consequences could be catastrophic. In March 1989, a much smaller geomagnetic storm knocked out Hydro-Quebec's power grid, leaving 6 million people in Quebec without electricity for 9 hours on a cold winter night. A 2013 report by Lloyd's of London estimated that an extreme solar storm could affect 20 to 40 million people in the United States and cause up to $2.6 trillion in damage, with recovery taking up to 2 years. Other studies have suggested even higher potential costs. This is why space weather forecasting has become a priority. Organizations like NOAA's Space Weather Prediction Center monitor the sun continuously, watching for solar flares, tracking coronal mass ejections and issuing warnings when space weather events might affect Earth. When a large flare erupts or a CME is detected heading toward Earth, warnings are issued to satellite operators, power companies, and airlines flying polar routes where radiation exposure is higher. Satellites can be put into safe mode, power grids can be configured to handle surges, and astronauts on the International Space Station can take shelter in more heavily shielded parts of the station. Humans have also learned to harness the sun's energy directly, technologies that are becoming increasingly important as we work to transition away from fossil fuels and address climate change. Solar panels, or photovoltaic cells, convert sunlight directly into electricity. The basic principle is the photovoltaic effect, discovered by French physicist Edmond Becquerel in 1839. When light strikes certain semiconductor materials, it knocks electrons loose from their atoms. These freed electrons can flow through the material, creating an electric current. Modern solar cells, usually made from silicon doped with small amounts of other elements to enhance their properties, have become remarkably efficient and affordable. The first practical silicon solar cell was developed at Bell Labs in 1954 and had an efficiency of about 6%. Early solar cells were expensive and found use primarily in space applications, where their lightweight and reliability made them ideal despite the high cost. The solar panels on satellites and spacecraft have powered space exploration for decades, but as manufacturing techniques improved and economies of scale kicked in, solar panels became cheaper and more efficient. By the 2010s, solar panels commonly achieved efficiencies of 15 to 20%, and research cells in laboratories have exceeded 40% efficiency for specialized multi-junction designs. The cost of solar power has fallen dramatically. In 2009, the average cost of solar electricity was around $350 per megawatt hour. By 2020, it had fallen below $40 per megawatt hour in many markets, making solar power competitive with or cheaper than electricity from fossil fuels. This trend is continuing. Solar power is now one of the fastest growing energy sources worldwide. In 2023, solar energy accounted for a significant and growing fraction of global electricity generation, and installations continue to accelerate. Solar thermal systems use the sun's heat rather than its light. Solar water heaters are common in many countries, using the sun to heat water for homes, hotels, and businesses. These systems typically consist of solar collectors, dark-coloured panels that absorb sunlight and heat water circulating through them. This hot water can be stored in insulated tanks and used when needed. Solar water heaters are simple, reliable, and can significantly reduce energy costs for heating water, which often accounts for a substantial fraction of a building's total energy use. Concentrated solar power plants use mirrors or lenses to focus sunlight onto a small area, achieving very high temperatures. These high temperatures can heat a fluid, producing steam that drives turbines to generate electricity, similar to a conventional power plant but using solar heat instead of burning fuel. Some concentrated solar power plants use molten salt as the heat transfer fluid. Molten salt can retain heat for hours, allowing the plant to continue generating electricity even after sunset, solving one of the main challenges with solar power: what to do when the sun isn't shining. Passive solar design uses the sun's warmth without any mechanical or electrical components. Buildings can be designed to capture winter sunlight through south-facing windows in the northern hemisphere, absorbing heat in thermal mass like concrete floors or brick walls. This stored heat is then radiated back into the living space at night, reducing the need for conventional heating. In summer, overhangs or awnings can be designed to shade those same windows, preventing overheating. Proper orientation, insulation, and design can significantly reduce a building's energy needs, making it more comfortable and sustainable. As the world faces the urgent challenge of climate change, caused largely by burning fossil fuels and releasing carbon dioxide into the atmosphere, the sun offers a solution. Solar energy is clean, producing no greenhouse gas emissions during operation. It's renewable, literally sustainable for billions of years until the sun itself changes. It's abundant, delivering far more energy to Earth than humanity could ever use. The sun bathes Earth with about 174 petawatts of energy, about 174 followed by 15 zeros watts. Total human energy consumption from all sources, fossil fuels, nuclear, renewables, everything combined is currently around 18 terawatts, 18 followed by 12 zeros. The sun delivers nearly 10,000 times more energy to Earth than we currently use. Even accounting for inefficiencies in capturing and converting that energy, and accounting for the fact that solar panels can't cover every square meter of the planet, there's more than a no. The challenge is capturing, storing, and distributing that energy efficiently and affordably. But technologies are improving rapidly, costs are falling, and solar energy is poised to play an increasingly central role in humanity's energy future. In that sense, we're coming full circle. For billions of years, all life on Earth has been powered by the sun, directly or indirectly. For most of human history, we used that solar energy filtered through biology, through the photosynthesis of plants that became our food and our fuel. Then we discovered fossil fuels, ancient solar energy stored in the bodies of plants and animals that died millions of years ago and were transformed by pressure and time. Now we're learning to use solar energy directly again, capturing it as it arrives from the sun, turning it into electricity, using it to heat our homes and water. We're becoming, once again, a civilization powered directly by the sun. The sun continues to inspire us in other ways too. Solar eclipses remain among the most spectacular sights in nature, events that draw people from around the world. A total solar eclipse occurs when the moon passes directly between Earth and the sun, blocking the sun's bright photosphere and revealing the much fainter corona. This can only happen during a new moon, when the moon is on the same side of Earth as the sun, and only when the moon is at just the right distance to appear the same angular size as the sun. Despite the sun being 400 times larger than the moon, it's also about 400 times farther away, so the two objects appear almost exactly the same size in our sky, typically about half a degree, across. This is a remarkable coincidence and one that won't last forever. The moon is gradually moving away from Earth, currently drifting farther at about 3.8 centimeters per year. Eventually, in hundreds of millions of years, the moon will be too far away to completely cover but for now, total eclipses are possible and spectacular. The path of totality, the narrow band on Earth's surface where the moon's shadow falls and totally blocks the sun, is only a few hundred kilometers wide. Within this path, observers experience a few minutes of daytime darkness. The temperature drops noticeably. The sky darkens, not to full night but to a deep twilight, with a strange quality of light that's difficult to describe. The corona becomes visible, a glowing halo of pearly white light extending out from the sun, streaming in delicate streamers shaped by the sun's magnetic field. Bright planets and stars may become visible. Birds and animals may behave as if night has fallen, with birds returning to roost and crickets beginning to chirp. Then, as quickly as it began, the eclipse ends. The moon continues its motion, and a brilliant point of sunlight appears at the edge of the lunar disk, the diamond ring effect, followed by Bailey's beads, bright points of light where sunlight streams through valleys on the moon's limb. Within seconds, the sun's photosphere is visible again, too bright to look at directly, and the corona fades from view. People travel thousands of miles, sometimes to remote and difficult locations, to experience a total solar eclipse. There's something primal and awe-inspiring about watching the sun disappear in the middle of the day, about seeing the corona with your own eyes, about standing in the moon's shadow. Eclipse chasers, people who've seen multiple total eclipses and travel around the world seeking new ones, often describe the experience as life-changing. And they're not alone. Historical records show that people have been fascinated by, and sometimes terrified by, eclipses for thousands of years. Ancient civilizations often interpreted eclipses as omens or divine signs. Chinese records mention solar eclipses dating back more than 3,000 years. Ancient Chinese astronomers could predict eclipses with reasonable accuracy, and legend says that two court astronomers, Si and Ho, were executed for failing to predict an eclipse in the 22nd century BCE, causing the emperor to be unprepared for the event. Babylonian astronomers in Mesopotamia kept detailed records of eclipses and discovered the Saros cycle, a period of about 18 years and 11 days, after which the pattern of eclipses repeats. In ancient Greece, the philosopher Thales of Miletus reportedly predicted a solar eclipse in 585 BCE that occurred during a battle between the Lydians and the Medes. The sudden darkness supposedly frightened both armies so much that they ended the battle and made peace. Whether this story is precisely accurate or somewhat embellished, it shows that by the 6th century BCE, some Greek thinkers understood enough about celestial motions to predict eclipses. Christopher Columbus reportedly used his knowledge of an upcoming lunar eclipse to intimidate indigenous people in Jamaica in 1504. When his ships were stranded and the local people were reluctant to continue providing food, Columbus warned them that the moon would disappear as a sign of divine displeasure. When the eclipse occurred as Columbus had predicted, the indigenous people were frightened and agreed to provide supplies. It's not a particularly noble story, but it illustrates how knowledge of eclipses could be powerful. Today, we understand eclipses scientifically. We can predict them centuries in advance with high accuracy. We know exactly when and where each future eclipse will occur, down to the second and the kilometre. The next total solar eclipse visible from parts of the United States will occur on April 8, 2024, with a path of totality crossing from Texas through the Midwest and Northeast. The next one after that, visible from the contiguous United States, won't be until August 23, 2044, crossing parts of the northern states. But even though we understand eclipses, even though we can predict them and explain them, they remain powerful emotional experiences. There's something about watching the moon slowly encroach on the sun, about seeing the last sliver of sunlight disappear, about standing in the moon's shadow and seeing the corona, that touches something deep in the human psyche. We are, after all, creatures who evolved under the sun's light, and having it suddenly disappear, even briefly, even for a reason we completely understand, is inherently startling and awe-inspiring. The sun appears in our art, our literature, our music, our mythology. It's one of the most universal symbols recognized by every culture. Claude Monet painted the sun rising over the harbour at Le Havre, giving the Impressionist movement its name. Vincent van Gogh depicted the sun in vivid yellows, capturing its warmth and intensity in paintings like The Sower and Wheatfield with Cypresses. The Sun, a painting in Van Gogh's late style, shows the solar disk as an intense swirling centre of yellow and orange radiating light. In literature, the sun has been a symbol of enlightenment, of hope, of constancy, of the divine. John Donne wrote, "Busy old fool, unruly sun, why dost thou thus through windows and through curtains call on us?" A playful complaint from a lover who wishes morning would not arrive so soon. Shakespeare referenced the sun countless times, using it as a metaphor for royalty, for constancy, for the natural order of things. But soft, what light through yonder window breaks? It is the east, and Juliet is the sun, Romeo declares, elevating Juliet to the status of the most important celestial object. Modern poets continue to draw inspiration from the sun. Mary Oliver wrote, the sun, and all we can become," expressing the sun as a symbol of possibility and transformation. Pablo Neruda addressed the sun directly in his odes, praising it as the source of life and light. The sun appears in films, in songs, in every medium of human expression. It's a symbol that requires no explanation, understood intuitively by everyone who has ever felt its warmth or seen its light. And as we look to the future, the sun remains central to our existence and our aspirations. If humanity spreads beyond Earth, which seems increasingly likely as space technology advances, we'll carry the memory of our sun with us. The generation ships or colony vessels that might one day travel to other star systems will be leaving the sun's light behind, venturing out into the darkness between the stars, searching for new suns around which to build new homes. Perhaps one day, far in the future, there will be humans or our descendants who have lived their entire lives in orbit around other stars, for whom the sun is just a piece of history, the star where our species evolved but no longer a direct presence in their lives. But even then, the sun will be remembered. It will be the star of our origin, the star that made us possible, the star whose light and warmth nurtured life on Earth for billions of years and gave rise to intelligence and consciousness and the ability to ask questions about the universe. Or perhaps, billions of years from now, some far future descendants will witness the sun's transformation into a red giant, watching from a safe distance on a colony world around another star, using telescopes to observe the star where their species was born as it swells and sheds its outer layers, creating a planetary nebula, leaving behind a white dwarf. It would be a moment of cosmic significance, the end of an era, the closing of a chapter in the long story of life in the universe. But that's all. Far in the future, so far that it's almost impossible to imagine what humanity will be like then, or even if something we'd recognize as humanity will still exist. For now, for today and tomorrow, and for billions of days to come, the sun rises every morning, steady and reliable, warming our world, lighting our days, making life possible, and giving us a beautiful reminder of our place in the cosmos. As you drift towards sleep, the sun is out there, 93 million miles away, burning steadily as it has for 4.5 billion years, as it will for billions more. And that is, in its own quiet way, profoundly comforting. Good night.